We are studying the importance of molecular orbital theory via the application of LCAO method to establish various molecular orbitals, arranging them in various energy levels, distributing the electrons in them, and finding bond order, number of bonds present in the molecule, and magnetic property of that molecule. Let us study carbon molecule.
We are studying homonuclear diatomic molecules. Let us study a diatomic molecule formed by element having atomic number 6, that's a carbon. Let us study C2 molecule, its formation. If we are studying the formation of molecule, then which orbitals we should establish? Yes, molecular orbitals. From whom can we establish those molecular orbitals? From atomic orbitals. So if 6 is atomic number of the carbon, then what will be its electronic configuration? 1s2, 2s2, 2p2. Now let us start from the first orbital. That's a 1s orbital. 1s orbital is a first shell orbital. It is an inner orbital compared to outer 2s and 2p orbitals. So when molecular formation will occur at that time, this 1s orbital will not interact with 1s orbital of other atom. Means though as per LCAO principle, first condition energy should be same is fulfilled, second condition symmetry should be same is fulfilled, but third condition appreciable overlap expectation is not fulfilled, and due to that those two 1s orbitals will remain non-bonding. There will not be any change in the electron density of these molecular orbitals, means orbitals in molecule and respective atomic orbitals, visually 1s in each atom. In this diagram, the orbitals established from 2s energy onwards are represented. So let us consider 2s orbital of one carbon atom and 2s orbital of other carbon atom. As per LCAO method, energy is same. Second, symmetry is same. Why symmetry is same I am saying? Because if you consider the 2s orbital and its rotation around the internuclear axis, z axis, cylindrical axis, the phase change will not be there. S orbital spherically symmetric. Throughout the s orbital there will be either positive phase or negative phase. Because of that it is sigma symmetric atomic orbital. These two sigma symmetric atomic orbital experience appreciable overlap to produce molecular orbitals. As per LCAO method, number of molecular orbitals is equal to number of atomic orbitals combining. How many atomic orbitals are there? 2. Molecular orbitals also will be 2. One bonding and other anti-bonding. Bonding orbital I am representing here as sigma 2s, which is obtained due to constructive interference. Overlap integral is greater than 0. More number of electrons are there between the two nuclei, due to which energy decreased. Repulsion decrease, attraction increase. Energy of sigma 2s orbital is relatively low than the respective atomic orbitals. On the other hand, antibonding, that's a sigma star 2s orbital, which can be obtained by subtractive interference, destructive interference. Electron density between the two nuclei will be less compared to atomic orbital electron density. Let us explain triplet of 2p sublevel, 2px, 2py, 2pz. Now this triplet, these three orbitals are present on each carbon atom. Their interaction we need to study. What do you think? If two atoms are approaching each other, out of these three, which orbital will experience more interaction, more overlap, strong overlap? Yes, 2pz orbital. Why? Because we are considering, it's our convention, Z is our internuclear axis, internuclear direction. So 2pz orbital, which is along Z axis, it will experience direct interaction with other 2pz orbital. Direct interaction means head-on head interaction. Because of that, the resultant bonding orbital will be of too much lower in energy. It's an expectation. Wait, you are not finding that in the diagram. I'll explain that. An antibonding orbital should be of too much higher in energy. And remaining two orbitals are there. That's a 2px and 2py in each atom. Those will overlap laterally. This 2px will overlap with 2px and 2py will overlap with 2py. Now one may be with the question, symmetry should be the same for molecular orbital formation. Then symmetry of 2px. What is the symmetry? Pi symmetry. Why I am saying it is a pi symmetry? What is a 2px orbital? One lobe is towards us, one lobe is away from us. One lobe will be positive, other lobe will be negative. If we rotate that px orbital around the internuclear axis, cylindrical axis, z axis, we will find one time the lobe away from us, if I consider it is positive, will come to the lobe towards us if I consider it is negative. So the wave functions will not remain the same during the rotation. So that symmetry is not around cylindrical axis, due to which we label that representation, we label that condition as pi. So we say the symmetry of 2px orbital of each atom is pi. Similarly, 2py orbital symmetry will be pi, because what is our 2py orbital imagination? The lobes are up and down. One lobe will be positive, other lobe will be negative. As I described for the 2px orbital, same case will be there 2py orbital. So both 2py and 2px orbital are of same symmetry, pi symmetry. Energy is same, that's our first condition. Symmetry is same, that's our second condition. Now what about the third condition? Suppose if I bring 2px orbital of 1 closer to the 2py orbital of other. It's actually only one orbital I can't bring. It's a cluster. It's a triplet of the orbitals. When I bring the two atoms closer together, just imagine the orbital which is towards us and away from us, that's a 2px orbital, an orbital of other atoms, say 2p orbital, which is up and down. Will there be any interaction? Because in between pz orbital is there, no? Pz orbital is experiencing the head-on-head collision, head-on-head interaction. So interaction between 2px and 2py is not going to occur. Overlap integral will be 0. But other interaction is possible. 2px of one atom and 2px of other atom can interact. 2py orbital of one atom and 2py orbital of other atom can interact. And that interaction we say as pi interaction because of their symmetry. And this pi interaction, I want answer from you. This pi interaction is weaker than sigma interaction or stronger? Yes, lateral interaction it is weaker. Because of its weak interaction, resultant bonding orbitals. Because of 2px and 2px interaction, I'll get pi 2px as a bonding orbital, pi star 2px as an antibonding orbital. Because of 2py and 2py interaction, I'll get pi 2py as a bonding orbital and pi star 2py as an antibonding orbital. Whichever the two bonding orbitals resulted due to pi interaction, means pi 2px and pi 2py, they are of the same energy. They are degenerate, but their energy is lower than the energy of respective atomic orbitals. I have represented those pi orbitals by green coloration. Let us talk about the energy of pi 2px, pi 2py and sigma 2pz. As per our general convention, energy of sigma 2pz should be lower than pi 2px and pi 2py because sigma bonding is a strong bonding, strong interaction, so bonding orbital should be of low energy. But what are we finding in this diagram? Sigma 2pz is of higher energy than that of the pi 2px and pi 2py. It is because the molecule, that's a C2 molecule, is formed from carbon atom whose atomic number is low. Only 6 electrons are there, 6 protons are there. Energy gap between 2s and 2p is small or less, and because of that, the sigma 2pz orbital is of the high energy. It is one of the general reason. But if you want to know the correct and clear-cut understanding, you go through the other video, making sense of molecular orbital diagram for nitrogen molecule, N2 molecule. Their concept will be more clear. Symmetric aspects are there. Those affects a lot to decide the energy of sigma 2pz. One need not to misunderstand that sigma bonding is a weak bonding, therefore energy decrease is low. No, not at all. Go through the video, you will get the clear-cut idea. But at second year level, if you could able to remember this, well and good. Out of curiosity, it is left to you. Now let us discuss about the antibonding orbitals. Since sigma bonding is stronger. Here you will find anti-bonding sigma orbital, sigma to pz, is of higher energy than the pi anti-bonding pi star to px and pi star to py. Both pi star to px and pi star to py are of the same energy. Those are degenerate. Why for? Because extent of interaction is same. So for bonding also degeneracy is there, and for anti-bonding also degeneracy is there. So if I have to talk about the energy levels for the molecular orbitals which are established due to 2p orbitals, the lowest orbital is a pi energy orbital, pi to px and pi to py. Next sigma to pz, next pi star to px and pi star to py, degenerate orbitals, and last sigma star to pz. Now it is a time to put the electrons in those molecular orbitals, because the chemistry of any molecule or element or ion depends upon its electronic configuration, and electronic configuration is in orbitals. Molecular orbital formation, their energies we understood. Now let us distribute the electrons. Total how many electrons are there in carbon molecule? 12, because atomic number of carbon is 6. So lowest orbitals, those are non-bonding orbitals which are not interacted, because those are inner. Which orbitals were those? Yes, 1s orbital. 1s orbital from each carbon will accommodate 2 electrons. Let us represent those electrons by k. So kk will encompass 4 electrons, and those electrons are in non-bonding orbitals. So we have discussed about the location of 4 electrons. Afterwards, the molecular orbital starts. Sigma 2s orbital can accommodate 2 electrons. Sigma star 2s orbital can accommodate 2 electrons. So previous 4 electrons in kk, and now in sigma 2s and sigma star 2s 4 electrons. Total 8 electrons we have considered. Still 4 electrons are left. Afterwards, energy levels are of pi to px and pi to py. As per Hund's rule of maximum multiplicity, the 9th electron will enter in pi to px. 10th electron will enter in pi to py in order to have maximum multiplicity. But still 2 electrons are left. Then there is no alternative, pairing will occur there. 11th electron will pair in pi to px, and 12th electron will pair in pi to py. So we are with now electronic configuration for carbon molecule. Can we find bond order from this? Yes, what's the formula for bond order? Bond order is equal to number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. How many electrons are there in bonding orbitals? 6. How? In sigma 2s 2 electron, and pi to px and pi to py 4 electrons. So 6 electrons in bonding orbitals. And in anti-bonding orbitals, how many electrons are there? 2. In which orbital? Yes, sigma star 2s orbital, 2 electrons are there. So what is answer for bond order? It is 2. Means double bond is there in carbon molecule. Let us elaborate that double bond. How many sigma bonds and how many pi bonds are there? Sigma bonds means relatively stronger bond than the pi bond. You will find those 4 electrons in outermost molecular orbitals are present in only and only pi orbitals, pi to px and pi to py, and because of the existence of electron in those pi to px and pi to py bonding orbital, 4 electrons are there. So bond order is 2. It means in carbon molecule 2 bonds are there, and both bonds are pi bonds. Interesting. See, till now you may be with the expectation first sigma bond should be there, then pi bonds will form. Here without sigma bond, pi bond is there. So mechanical study is not important. Actuality, reality is important. Only mere weak pi interaction also is enough to form the C2 molecule. 2 pi bonds are there. Then you will be with the question, why not I am talking about the electrons in sigma 2s and sigma star 2s for bonding. See, whatever the assistance is done by the electrons in sigma 2s is opposite or completely or exactly by means of the electrons in sigma star 2s. So I am not considering the sigma 2s and sigma star 2s to decide the bond order at this moment to describe the number of bonds. Okay, how many unpaired electrons are there? No unpaired electron is there in this C2 molecule. If there is a no unpaired electron, then what will be its magnetism? It is diamagnetic in nature. Let us understand its electronic configuration, representation. See, C2 molecule is represented, and 3 horizontal line means equivalence. In special bracket, orbitals and electrons are represented. coding I informed to you. By green-blue coloration, I represented the non-bonding orbitals and electron present in them. By white color, I represented bonding and anti-bonding orbitals. But electron present in bonding orbitals, I represented by white color, and electron present in anti-bonding orbitals, I represented here by yellow color. Total 12 electrons are there. First 4 electrons will be non-bonding K shells. That's a oneness orbital we are considering. It's the first shell, 4 electrons. Then in sigma 2s, 2 electron. Sigma star 2s, 2 electron. Pi to px and pi to py are degenerate. Therefore, in between equal to sign is there. Each orbital has 2 electrons. In sigma to pz, no electron. Pi star to px and pi star to py are degenerate, are of the same energy. Therefore, between them is equal to sign is there. And each orbital has no electron. And highest energy orbital, sigma star to pz, has no electron. As a homework, simple 2 questions. You have to mention bond order and magnetic property of diatomic carbon, means C2 molecule. Waiting for your answers in the comment box.
Yes, in detail the application of molecular orbital theory for carbon molecule, C2 molecule you understood. But let us compare molecular orbital theory results with the valence bond theory. Electronic configuration of carbon 1s2, 2s2, 2p2. In 2p orbital 2 1p electrons are there. So when 2 carbon atoms will come closer, at that time 2 1p electrons will establish 2 bonds. So there should be 2 bonds in the carbon molecule. Same is the concept explained by molecular orbital theory. But valence bond theory could not say what kind of bond it is, sigma bond or pi bond. That's the importance of molecular orbital theory. What about magnetism? Valence bond theory says C2 molecule is diamagnetic because there is a no unpaired electron, and same explanation is given by molecular orbital theory, and that's the reality. So molecular orbital theory is more towards the reality than valence bond theory. That's the importance of molecular orbital theory. Let us study application of molecular orbital theory for next molecule, that's a nitrogen molecule, N2, in next part.